This video continues a set of videos that I'm making for my data abstraction class, and we're talking about pointers. And in this case, we're going to talk about making pointers and how we get a hold of pointers. And so in the last video, we talked about creating variables and how to picture that and what a pointer was. We said that a pointer just stores an address in memory for where something is located, and we can follow that. So what I want to do in this video is I want to actually start writing some C++ code, and we're going to write just a little program that creates some pointers and prints out their addresses. So since I said I'm going to have to print stuff, I will start by including IOStream. I will say that I'm going to use cout so that I can use the shorter name for it. And we'll go ahead and make our main. I'm not passing in any command line arguments. Make sure to give it a return value. And we'll start off with our int a being initialized to 42, just like what we had before. Now I want to make a variable that is a pointer. So this syntax here declares b to be a pointer to type int. One of the common questions that people ask is which side should the space go on, and it turns out that to C++ the answer is it doesn't matter. This is completely a style issue. However, I prefer the style of having it close to the variable for the simple reason that if you type something like this, if you put the space over there, this declaration now looks like you're declaring two int stars. Both B and C look like they should be pointers to integers, but it turns out they're not. It turns out that star is only associated with the B, and the C is actually just a plain old int. And so personally I feel that putting the space over here makes it look more like the pointer is associated with B, and so it kind of makes sense that C is an int. In practice, you should really just only declare one variable per line, and then this isn't a problem. So I want to initialize B to be a pointer. So how do we get hold of pointers? There are two basic ways that we're going to do this, and how we do it tells us something about where we get it in memory. So I talked about the fact that there are kind of two ends to our memory here. We have the stack, which is where our local variables are allocated. So A is definitely on the stack. Turns out that B will be on the stack as well. And then we also have the heap. Now in C, you get memory from the heap using the malloc command. In C++, you will typically do this with a call to new. I want to get a pointer to A though. I want to recreate what we had in the picture where B is going to store the address of A. And a single ampersand in front of an expression gives you and it has to be something that you can get the address of, gives you the address of that value. So this sets up B to be a pointer to A. And so all I want to do here is print out the value of B. We can compile this program. Note that in order to compile this with G++, currently I have to say that I'm using the C++ 11 standard. That is because this particular form of initialization does not work with older standards. So if I run this, we get this address for B. It's a big hex number. And we can tell that the machine I'm running this on happens to be a 64-bit machine, because otherwise you would never have more than 8 hex digits here. Those are, let's see, yeah, that is your lower 8 hex digits. If we were on a 32-bit machine, that's all the digits that we could have on this, but we're on a 64-bit machine, so we can get a much larger number. What about the other way of creating a pointer? Well, I can create a pointer C and set it equal to a new int. Okay, so what this does in our picture here is calling new int allocates a chunk of memory like this, though we didn't give it a value, so the 42 wouldn't be there. And it gives us back a pointer to this. So we wind up having C here on our stack, and the value stored in C is whatever pointer. So C is a pointer to something, and it turns out that it points to this memory right down here. Okay, so that is what this line of code does. It creates a pointer, a variable on the stack named C, that happens to store the address that is returned by a call to new. Just like with malloc, if you ever malloc something, you have to free it. If you call new, you need to call delete as well. So the last thing I want to do here in this video is then print the variable C. So if we compile that particular code and we run it, we now get two pointers. Note that the location of B is different here. Okay? It does not have to be the same from one run to another. That'll be significant for things that we talk about later in the semester. The fact that pointers can basically be wherever. They're generally in similar spots. I mean, you'll note that this number and this number are not too far away from one another, but they're definitely not the same location. You'll also note that C is in a very different part of memory. Okay? This is a much smaller number for C than for B. And indeed, when I drew my pictures here, it was intentional that I put the heap on this side and the stack on this side, because that is how things are laid out by the GNU compiler. You typically have the stack growing from high addresses and getting smaller. And we'll come back in the next video and we'll actually verify that the stack grows towards smaller numbers. The heap, on the other hand, doesn't have that much order. You might get things getting larger for a while, but then after the program is run, you could get smaller values again. The heap, as the name implies, has much less structure to it. So we'll come back in the next video and we'll just look at memory addresses when we have the call stack involved.